Can you hear me? Okay. All right. Any questions? Anybody? No? All right. All right, good. Let's start. So in the homework, right? You have a bunch of functionals like this guy. So like u squared and u prime squared. And the question is to find the Euler-Lagrange equation. So let me do this one. We'll do a bunch of examples. And I asked you to do part A and B. So do all the parts the easy way, okay, which I'll do now. But then do just parts A and B a little bit harder, just to understand what's going on at the back. I want you to take the fractional, the variational derivative like I did in yeah. So I want you to do this guy for parts A and B, okay? Or I don't know, you'll see when you get there. Anyways, this is for next week stuff. Yeah, anyway, so that's what we did last time. But now I'm just gonna use the result to get the same ODE. So we got an ODE last time over here. We got this ODE, meaning that the minimizers, the solutions of this guy are minimizers of the following optimization problem. Min of the functional u squared, u prime squared over all u with u0, u1 equal to 1. Is that okay? Okay, good. So this is a minimization problem, and I will prove today a theorem that says that the minimizers are always given by an ODE, which is called Euler-Lagrange. Okay, all right. So let's do that. Let me show you how to apply the theorem. Here. All right. So let's do it for this case, just to see if you understand. Can someone tell me what is LZP? Sorry, LXZP for this functional? Any ideas? And whatever. No. Here or Zoom people, do you know? Huh? What? Yeah. So Zoom, do you know? Andrew? Yes, thank you, Michael. Good. No, there's no X. No, because you have to match the variables, right? So Mike, yes, perfect. All right. And then you take this derivative. So let's do it. So first you take L partial Z, which is, you said the last, yeah, what is it? Yeah. And partial of P. And now let's find the ODE. So, so you plug in Z equal to U. Okay. So you plug in Z equal U and P equal U prime. Okay. So now, okay, I want to have it on one page. All right. So I have minus d dx of LP, so 2p, evaluated at p equal what? Yeah, u prime x plus 2z evaluated at z equal, yeah. And you set this guy to 0. Remember? Is that okay? Okay. So the first guy is minus d dx of u prime x. And this guy is equal with a 2. And then 2 times u of x. Yeah. And so what do you get? What's the ODE? Set it to 0. Yeah. Okay. What's the ODE? Yeah. So, which is what we got before, right? Yeah. Okay. So that's all I want you to do for question 15, the homework, for all the parts. But for parts A, B, I want you to do what I did with the variation. Okay. Okay. Good. Everybody happy? All right. Okay. So now I'm going to prove this. So you don't have to prove it besides parts A and B. So you can just use this, that this is always given by this Euler-Lagrange, the minimizers. So these guys give you the minimizers. So this is minimizers. Okay, let's go. Yeah, so if this guy is there, together imply, yes, equal to 0. Yeah, okay, good. So yeah, I have to assume C2 because here you take you have one derivative inside the Lagrangian and you have another derivative outside. So you have to take a double derivative, okay? So that's why I assume that the guy has 2 derivatives, C2. But yeah, whatever, you can relax it. We're not gonna go into that. So what do I have to do? Well, remember, what is variational derivative? Oh, I jumped too much. Variational derivative was this guy over here. So this is the directional derivative. And remember we had this formula that this guy is equal to AB, and then you have your g of x, and then you have vx, right? And then we call this gx to be the variational derivative. Okay? Okay. So yeah, so this is a bit of a long proof. We go step by step. So my definition of my function will always be of this form. Okay, it will always be like this. And what did I do? I subbed in my perturbations. Okay, so I put in my perturbation. over here. So perturbation. And in the next step, it's called the Feynman. It has many names, but it called Leibniz derivative under integral. Okay. We did this in analysis. It requires quite a bit of justification to be able to swap. You see, we swapped the two, right? And that's not obvious at all. But it's beyond our course. You're welcome to come to analysis. Yeah. Okay, I mean, I'll write the name. It's called, yeah, it's the one I just called here, Leibniz differentiation under the integral. Okay, so if you want to look it up and understand what happened, look up this thing. It's a theorem. All right. So you do that. I mean, oh no, it is ugly. Yeah. Then what did I do here? I mean, I did chain rule, sure. But this is called also a total derivative. We did this in office hours and it took us like 20 minutes. So you have, whenever you have a function, so you have a function of three variables here, L of x, u, x, and plus sbx, and then u prime, sv prime. Then when you take DDS, you have to take DDS of each variable, right? So I do it the first guy, I do the second component, and I do the third. Okay? Is that okay? All right. But then x is just a variable. I mean, it doesn't depend on s. So it's 0. So that guy's out. That guy's dead. And so you're left with these two. And let's see, we're almost done. So now all I have to do is factor out the v. I need to make this into a v. Okay. And how do I do that? What's your guess? Without looking at the slides. What's your guess? How do I turn this into a v? Yeah. So we do yeah, integration, yeah, integral by parts. And so I do that. And what happens? This is nice. But then you pick up a boundary term. But luckily, what do we know about the v of a? Does anybody remember? Whatever. Yeah, anyways, that was the definition of test functions, okay? So, whatever. So this guy is dead also. That's why. And that's it, really. I mean, I have my two guys. I factor out the, come on. I factor out the v over here. And by the, whatever, the first, by the first order condition, this is 0. So what can I get? Which lemma do I want to use to get my ODE? What was it called? So that you can just write it during the thing. Yeah, FOC, which stands for fundamental. What do you think the O is? It's like Jeopardy. Fill in the blank. What's O? Off. and then what's the C? Yeah. So again, just to remind you the result, because I want you at least know that. if you're gonna do this, yeah. So whenever you have some function, call it g of x, and you know that this is always 0 for all test functions. So for all guys that satisfy this, then g of x is identically 0. Okay. So we did this with this epsilon delta argument, which you call it lambda epsilon. Yeah, no, epsilon lambda. That was your, yes, good. All right, any questions? That's really the main result. And okay. So yeah, and that was our definition of the variational derivative. Anyways, I think I mixed up the. This should be the other way around. Makes no sense. That's weird. Okay, I'll fix it. Right, so now let's do an example just to, get some practice. So here's the functional, and you'll see that its minimizer, if I remember correctly, is not C1. I probably have it. Okay, whatever. We'll see what. I don't remember now. Yeah, this is my functional, and I'm going to give you the Euler-Lagrange. Yeah, let me draw the function. I mean, I want to find the equation first. Guys, find the equation first. Yeah, let's just do that, guys. It's more fun. So can someone tell me what is LXZP equal to? What's the Lagrangian? Zoom people and here people. Zoom people? What do you think? What is it? Yeah. Good. Was that Michael? Oh no, Andrew. Good job, Andrew. Yeah, z squared 2x minus p whole thing squared. All right, now let's find the Euler-Lagrange. What is L of z? Or yeah, that's how they write it. But they want to say partial z of L. What do you think is what is that? Yeah. And then what about LP? Yeah. So this, yeah, let me put it outside. Huh? Good. Now, what do I want? Yeah. So my Euler-Lagrange is ddx of L's. No, I want to memorize this. What did we do? The last guy was yes, and then L of z. Now, and I plug in z equal to what? Yeah, and p equal to, yeah. Okay. I want more space. All right. Anyways, so okay, let's go. minus d dx of what? 2 times. Okay, good. I think you're getting it now. So then it's oh, but there's a minus, right? And then LZ is 2u 2x minus u prime. All right. I mean, it looks terrible. I don't know. I mean, yeah, that's the idea. I don't know if I want to simplify it, but at least the minus is not there. So they kill out. Did I get this right? Okay, we'll check in a second. Yeah, and the claim is that the minimizer, the solutions of that ODE are given by functions that look like this. So it's flat, and then it goes like this. All right. Okay. All right. Let's go. Did I get the, yeah, so this is the one, we got that, and the minus, good. Anybody talking now? No. And then, yeah, that's the ODE, all right? And then, I don't know, how would you do it? I can put it in Wolfram Alpha, I don't know. But what did I do afterwards? I don't know. I see, I see. So then, yeah, this is a little bit of work. I have to prove to you that the solution of this guy is given by this ugly looking function. Okay, by this guy. So let me verify it for x non-negative. So when x is non-negative, I want to show that the minimizer is given by x squared. Okay, all right. There's no minus. 2 times x to the 4, 2x minus 2x, so it's 0, right? Yeah, okay. So this guy is dead. And then you have 2x squared. This is again dead. Yeah, so these are both dead. Okay, so it is a solution in a stupid way. And but then the zero function is also a solution. So for x negative, if you put u star equals 0, what do you get? So you get d dx 0 stuff, and then plus 2 times 0 stuff, which is again 0. Okay, so now why am I talking about this? So we just showed that u star is given by 0 and x squared. Okay, but then if you take two derivatives, what's the second derivative when x is non-negative? 2. What about here? 0. So is this continuous? Is it a continuous function? Yeah. What? What are you talking about? No, I'm talking about u prime, u double prime. What? Sorry, what? Yeah. So it's not continuous. So not continuous. So U star is not C2. Anyway, so the point is the result we just proved. There's a weaker version of it, but it requires more machinery. Anyways, let's go. All right, more examples. This goes under the name geodesics. I should have written this. Being really probably have to learn this when you go and do GRE. This would be your first, yeah. So I want to go deep. We will have a little bit of one class. We will do rate of convergence, but I want to go into geodesics a little bit. So, anyways, this is in the book. Okay, so in the plane, it's easy. The question of, suppose I give you 2 points, and I ask you what's the shortest path that connects them? Is this the straight line? But what if you are, if you are in some other object, like a cylinder, and I give you 2 antipodal points, what do you think is the shortest path? Yeah, we can do it with your hand or your pen. Oh, no, but let's keep it normal. I mean, I think yes, you're getting close. But visually, like, what do you think? What's the closest path? So you, oh, I see. Yeah, it is a little bit difficult, isn't it? Okay, yes, you're right. Let me think. No, I said antipodal. I said antipodal. So it's easy. You just take the equator. Yeah. Otherwise, it's a little bit hard. You have to have some tilted. Anyway, so this is a geodesic, okay? And people want to find the curve. They want to, given some constraints on your geometry, this is the functional, give me the path that minimizes the distance between them. Okay? So, yeah, good. So yeah, this is yeah, I want to explain to you because many of you might not have taken geometry. So where did this come from? So a way to write this as is 1 plus du dx. You factor out the dx. And then you have dx over here, they cancel out. So you get square root of dx squared du squared. Does this remind you of anything? What's the, if I give you 2 vectors in R2? Yeah, what? Yeah, so it's the Euclidean distance. And what was that? If I give you 2 points, distance of A and BB is given by what? Yeah. Good. All right. So all it says is I want to minimize the Euclidean distance, and I want to, in the future, come back and do the more complicated stuff. So instead of just Euclidean, you add what is called curvature, and it shows up here. But we'll come back to it. So usually when you want to, when your geometry is different, you pick up a factor over here because you do change your variables. So you change from like a flat guy to like the sphere or the cylinder. And if you remember from change of variables, you get determinant of Jacobian. And that's basically, this is like determinant of Jacobian of the change of variables. It's really that simple. It's not very complicated. All right. I want to do the cylinder example next week. All right. Okay, I wish I asked you, but okay. So this is my functional, and I want to minimize over all points, over all paths that take A and connect it to B. Okay. Okay. All right. And we will prove that it's just a line. The Lagrangian is given by this. Let's do it together, right, Bert? So what is L of Z? Yeah. What is L of P? What do you think? Well, let's do a little bit simpler first. What is the derivative of square root of x? Is that okay? So you just do chain rule. So you get your guy. And then you do chain rule. So you get 2p. So yeah. All right. And let's go. So then you have minus d dx LP for P equal to what? Yeah, U prime. Plus 0, right? Okay. So then you have minus d dx of U prime over 1 plus U prime squared. All right. So yeah, this is LP and this is your OD. It looks absolutely terrible, but we will try to solve it. So one thing that, yeah, so here we're kind of lucky. LZ was dead. That's very nice. So that means that you have a derivative guy. And remember from first year, it says that whenever you have f prime to be 0, f needs to be constant. Yeah, so that's all we're saying here. And now I want to find U prime. I want to find, I keep writing W. I want to compute. Yes, I want to compute U prime. Any question? Yeah, so then, okay, so yeah, I isolate and I have one unknown. Okay, I can show you, but we can do it together. So call this guy Y. What do you think Y is? I don't want to keep looking, I'm bored. So Y is equal to, yeah, what do you think? I mean, don't look, I can look as well. What do you think? What is Y? What's your guess? What? So yeah, we have to assume, first of all, so what can I say about C just from here? Can we figure out some things about C, like the domain of C? Like roughly. What do you think? Yeah, it has to be less than 1 and it has to be positive, right? So it has to be strictly less than 1. so then I'm allowed to bring this to the left and divide by 1 minus c. Is that okay? Is that okay? All right. And now you do your square roots, but this guy is positive, so it's fine. And anyways, from here I think it's clear. We just integrate. Yeah, so you have u prime equal to this c square root of c 1 minus c, and I just integrate. So I get this linear guy, which is exactly what we expected to get the line. So let me find the alpha and the beta. So we have that u of a is a, and u of b is b. So I have the following system, too many alphas. So this is alpha of a. I hate this. No. What's another good notation? Maybe like px plus q. I don't know. Okay, well, who cares? So this is p of a plus q is a, and pb plus q is b. Two unknowns, two equations, and do I want to solve it now? Where? So okay. Oh, I missed my slide. Good, we'll do it together. So okay, let's go. Is there an easy way to do this? Maybe subtract them, right? So you have p of a minus b is equal to a minus b. So I get p, right, which is the slope from high school. And then q, I know it's equal to pa, no, yeah, a minus pa. Oof. So it's terrible. That looks terrible. It is what it is. So then, will this work? So it says that the guy who connects AA to BB is given by the line y equal a minus b, abx, and this is the intercept. Do I have to write it? I mean, that's the intercept, okay? Does this line connect the two? So let's, I mean, I know that this is the right slope, but I don't remember the intercept. Sorry, what? Oh, does it have a nice formula? No, really, don't rush. So you said it's big A? Sorry, what? Times small b? Oh. Oh, I think I know what you're saying. Yeah, there's a cancellation. So let me do it. So you have A minus AB minus AA plus BA over A minus B, and these two guys cancel out. Oh, I see. All right. I should have done it. All right. So this is B minus A, and this is no. So I mean, it doesn't seem. Yeah, I mean, all right. Yeah, okay. Anyways, so let's check that this is indeed, I want to check that this connects the 2 points. So what you have to do is you plug in x equal little a, you're supposed to get big A. So let's go. Let's do it. So if you plug in x little a, which looks terrible. Oh, I liked it in the other form. I was right. No, you made it worse. It was way better because now the cancellation is immediate. Yes. I mean, it's only easy in one case. In the other one, your formula is actually better. So you have a b a plus a minus a b a, and they cancel out. So you get a as expected. And then I don't want to do the other one. You could do it. But anyway, so this guy will connect it's just a line connecting the 2 points. All right. Now you get me curious. What if I put x equal b? So I got ab plus a, and this guy is the same factor. Oh, I see, there's a cancellation. So you have a minus b, but then you have b minus a plus a, right? So you get b plus a minus a, so you get b. Okay? All right, good. Who cares? I only care about this. I don't know why. Too addicted. Okay, well, any questions? Other one works too. Yes, thank you, Daniel. Other crazy people like me exist. All right, let's do more examples. Oh yeah, we're gonna do the cylinder now. I like that. So yeah, the surface of revolution of U formed around the x-axis. Can anyone tell me how to draw this? How do you think it looks like? So here's the x-axis. Yep, very good. Yes, thank you. Like this guy. From A to B. Okay. All right. So you see, I have my Euclidean distance, and this guy over here is my change of variables. I want to see a little bit how I got this. So might be too much. It's okay. It's a little bit much. I'll do it next week. Oh, no. So this is second year calculus material. And if I give you some graph, then yeah, you get this base. No? Is that okay? Yeah. So this is the surface of revolution. The other one was when U of X is just constant. Yeah, you get the base. And apparently, I don't remember how you get this. I can probably do it by hand. No, I don't want to do it. So the surface area of this whole thing, can we eyeball it why this is true? So this is, yeah, okay, go ahead. Right. So if U of X, that's right. If U of X was constant, I guess what I'm trying to remember, how do we get this? This is the Jacobian, right? The slope? Yeah, this is the Jacobian, right? The change of variables, right? So it should be something like, okay, I don't know, whatever. We'll do this again. Yes, okay. No, I have to stop. So yeah, the Jacobian is given by, sorry, the Lagrangian is given by this function, because whenever you see u, you put z. Whenever you see u prime, you put p. Okay? Can someone tell me the easy one first? What is LP? We did this. You did this. What? What? Yep, perfect. And then LZ, because does anybody remember? It's a little bit harder. Let's split cases. I know. So you have to look at the sine function. So yeah, the function is 2 pi z 1 minus p squared. And then let's say z is no negative. It will be what? Yeah. And then what about negative? Yeah, good. Oh, there's no z. Yeah. Yes, I do. Yes, thank you. Because you have a kink. Yeah. So it's not differentiable. So this guy is equal to, yeah, you want to say the sine function of z, but without allowing 0. So 2 pi. Okay. Well, no 0 allowed. Happy everybody? Perimeter x, small length. Well, what do you mean? I think you're talking about. Yeah. So yes. What are we talking about? Yeah, z is u, and yeah. So you're not allowing z. You yes. So we're only looking at the case of a no negative. Okay. So that's your guy. And we just computed that. So before I do it, I want to do it with you. So d dx of LP at P equal what? Huh? Yeah, you prime. And Z equal, yeah. And all right, is this, no, it was terrible. I don't know what I'm doing. Yeah, I mean, good. And then it's disgusting. Yes, good. And you set this guy to 0. All right. And shall I keep going? No. We'll do this next time. Okay, thank you. I don't want to. It's too much. Yeah, I will take all your time. I know. I don't want to do it. Sorry, what? Can you use your mic, Andrew?
Sure, yeah. Because it's just that we just need to find a
Andrew?
continuous function that does this. Yeah,
No?
can you hear me? Hello?
Okay, on the full screen, oh, you are?
Yeah, hello. Hello.
Can you try again?
Hello, can you hear me?
Okay. Can you try again?
Can you hear me?
It's always me, isn't it? Okay. Says external microphones. Hello?
Hello, can you hear me?
Okay, good.
Yeah. So we only require that U is continuous. So can't we just have it like be zero almost everywhere, but then spike at the points A and B to satisfy our requirements?
Okay, let me see. Are you talking about this example specifically?
Yeah, because we just want to find something that has the smallest surface area.
All right, let's see. So you say put zero, I put zero, but then it's not zero, right? You get 2 pi.
But like if I'm not like intuitively,
No. Let's
I
just
would
look at wait. But let's look at the ODE here. You see that it doesn't satisfy it, right? If you put u equals 0, you're left with 2 pi, right? I will come back to what you're saying, but is that okay?
I guess yeah.
No, like put u 0, 0.
Yeah.
Okay, good. Now, what were you saying? So you have this vase, and then,
So like
but wait, what
so
was
if
the
we have
question?
2
I
points.
forgot the question. The question says to minimize this over minimal. I see, and the solution should be the cylinder, right? Like the solution should be the given all vases. This should be the
Like
minimizer.
my idea is just because we only require it to be continuous, just make it like a very
No.
a smooth
C1
wave,
means
not
differentiable.
differentiable.
C1 means
Oh,
differentiable.
oh, okay, never mind then. I see.
I mean, we can't even take derivative.
Yeah, yeah.
Okay, were you trying to break it? I don't understand.
Well, I was like, I guess maybe I was thinking something like a bump function at A and B that
Uh-huh.
decreases extremely fast. So it's around A and B, it's non-zero, but everywhere else it's zero. But then, yeah, that's not differentiable.
Why would you want to do that? To minimize what?
To
The solution
minimize
size?
the surface area, because if you revolve it, then where it's zero contributes basically nothing.
And why is it not differentiable? The one you mentioned at the corners, right? Yeah, I think.
Yeah, I think
Yeah,
it's at the
like
corners.
because if you use something like this guy, I remember this guy is differentiable, isn't it? Am I? I'm probably wrong. Oh no, it blows up. You see, Andrew?
I can't see your screen. I just see the slide.
What do you mean?
I only see the PowerPoint. I think you're sharing the screen.
Can you see?
Yeah.
So if you use the bump function, and you take derivative, you get this guy,
Mm-hmm.
and this guy indeed blows up when x goes to 1, right? Well, actually,
Yeah.
no, sorry. When x goes to 1, it goes to 0, right?
Yeah, it goes to yeah.
So you want to use, there should be some problem with what you're doing. Let me see. So you put, what was our function space? Our function space was UA is A, UB is B, and then you said, So I guess the picture you have in mind is something like this, right? Like this and like this, right?
Yeah.
So at A, you're A, at B, you're B, and then, yeah, but you see you have a lot of mass over here, right?
Hmm.
Um, it's not obvious. Do you really not have differentiability? I'm guessing, yeah, you probably don't have it in one of the corners. So your bump function, yeah, you know, like exactly like what, yeah, I will have to see the function because I'm not sure. Hmm. Yeah, I don't know. That's an interesting observation. No, I mean, bump functions can be differentiable, so that's not really. Okay, I mean, I don't know. What was the minimizer? So the minimizer was what? Yeah, so I have this crazy looking cosine.
It could also be because if you have two bump functions, it's very hard to fix values at two different points.
No, I mean, is it? Why? Because like, have your guy.
Oh yeah, it's zero outside. Yeah, never mind.
Yeah, like, scale it.
Yeah.
Yeah, so multiply your guy by, yeah, I don't know. That's a very interesting question. You're saying concentrated very close to the guy, and then I don't see what the problem could be. Like in the functional, something has to blow up, you know, like something over here will have to blow up when you do this. I don't know what. What could it be that blows
I think
up?
yeah, when you make your thing smaller and smaller,
Uh-huh.
the derivative blows up.
The derivative blows up, eh? Because exactly, yeah, I think you're right. Because you're asking it to do like a sharp turn.
Yeah.
I mean, let's do it because I know the bump function is like this, right? So 1 minus x, and then the derivative of that, you just get polynomials of it. That's interesting.
Oh, I think it should.
Is there a
It should be
mistake?
1 minus x squared.
Yeah,
Yeah,
that's
1
what I
minus
did.
x squared.
Yeah,
No, as what?
right?
I forgot if the square was inside or outside.
It's outside because you do chain rule,
Yeah.
and the minuses cancel out. I mean, there's probably another minus somewhere, something like this. Yeah. From the is this big? This goes to 0, doesn't it? But I think you're right. When you make this up, when you make this like sharp turn, I'm guessing somewhere over here, because it should be like really big, right?
Mm.
Something should happen. Yeah, can you play with it? Actually, if you're interested, I mean, it would be nice to see exactly. So this guy, what I'm writing is, so I want b minus x, a minus b, a minus x. Sorry, x minus x. So this guy is a bound function at a b, right? And then at 0, you want it to be, I guess, a or whatever. I don't know. Can you play with it if you're interested? It would be
Yeah,
nice.
I'll try.
Any questions? Oh, Daniel. Daniel, use your mic. I mean, I can't read the. So 1 minus x, which way you go to 1? From one side, you go to minus infinity. From the other, it's infinity. No. We take x in 0, 1, right? So, and you come from the left. Daniel. Where's Daniel? Daniel. Right. That, yeah, we're not, yes, and there's a second order. But I don't really see it much. Euler-Lagrange, like if you do. Yeah, you need like convexity. So you have to look at the second variation. Same stuff, huh? Yeah. No, we're not gonna do a second. I think we talked about it. It's like the action. Remember you mentioned it. Yeah. I mean, it has like, huh? Wait, wait, now you're asking, oh, I see what you're asking. You're talking about the, yeah. No, I mean, the least action principle is what I just proved. That the minimizer is given by this Euler-Lagrange. So you have what does least action mean? It means you have a conservation, right? So this is the. Like, let's go back to that. There was a nice, yeah, the Brachenstrom, whatever. Yeah, like here we had to use. No, it's fine, I fixed it. And I think this was Lagrangian, right? So let me. That's a little bit different. What? What do you mean? So if I remember, so at the back you have a Hamiltonian, right? And this equation implies conservation of that Hamiltonian. Okay. Huh? Yeah, so you have so yeah, so you have a Hamiltonian. So yeah. Yeah, Q is momentum. No, P is momentum, right? And Q was position. Yeah. But anyway, so I remember, like once you have this, you get conservation. Like with your line integral, you do like a Green's function thing. I don't know. Do you remember? But there was some conservation, right? I remember there was. Like, I mean, that's the one I talked to you about. Like for simple systems, it's just like kinetic plus potential. Like you're supposed to get, wait, I think I passed it. Yeah, so you get conservation. So there's this beautiful Noether theorem. Have you heard about it? And that's how you get your, that's a different way to get, yeah, Euler-Lagrange. So, no, it's the, I mean, you asked me why are we studying Lagrangian? And, okay, yeah, this is the one you talked about. Right. Yes. So, okay, that was a little bit too long, but that's what I remember that. So. Yes, so that would be different. So the concentration in time of the Hamiltonian gives you apply Noether theorem, and you get your yeah. So it's the exact same thing. You take a variational derivative. If you look at the okay, this is the stationary, like what is it? So yeah, but stationary they will win, right? So you want to find minimizer of this. So you are, huh? Yeah, but you want the solution to the Euler-Lagrange. And yeah, this is the action function. No, it's not pure math. Honestly, I understand the Euler-Lagrange, but I don't understand the thing they wrote here. This summation, which is basically momentum times velocity. What is that? Acceleration or something? Like Newton's law? Like 2 times mv? No. Like how do they, why are they looking at, like you say, why are they looking at this? Oh, no, I want to know actually. Why it's t minus v? So why is it? So what is this mathematical? Oh, wow. We're actually gonna do holonomic. We might get answered. Okay, so what? So what? Yeah, I mean here, yeah, we're doing very general stuff. But I don't know, like the physical, and I know mathematically why, but I don't know why. Okay. Again, I mean, this is the. Oh, wow. But what would be the lambda? What would be the multiplier? Oh yeah, I talked about this last time. Yes, yes. If you discretize the integral, you are the u and u prime are the constraints, right? You have like a So what was it? So you minimize. No, it's more complicated. Why is it lambda? Oh, the Lagrangian is not, I know it's not that, but why does it turn out to be? Yes, you get Euler-Lagrange. Then you get, okay. I mean, all these guys start from what we have, right? Euler-Lagrange, right? You see, like they start from Euler-Lagrange and they prove that it's T minus V. But then what, and when they say answers, it means a guess. So they guessed it. But how do they know? And it says it does not have physical significance. I didn't expect that. I thought it had some. I mean, okay, I don't know. I thought it had some meaning. Because I heard action all the time. Like if you read papers, people are very interested in the action, like the action inside the integral. And you but you always start with the Hamiltonian, and then yeah, it's the same action, but here your group is simpler than that. You just have vector space operations because you have a function space, and adding two elements in the group gives you another element in the group. That's like the conjugation, right? Remember when you want to go from one element to the other? You know what I'm saying? In a group, right? You have like you have some operations. Right? Some group operations. So here we're using the group of the function space with yeah, plus minus and the space. So we is still in space. So that's the group. And wait, what is the group? I mean, group action just means like this is a group action. So, the multiplication of the random, right? C times B. So instead of y, we mark it to B, what does it have? So there's another reason. No one will see it by C. Like we have the first order plus then no, yeah, this was a typo. Supposed to be you. Yeah, that was a long email. I didn't have time to read the whole thing. It was like, I'm like, this is class. You can just talk to me. You didn't have to like send me a. But so what is the one? A reference method? For what though? Project in what? And what do you like to do? Like, this one, like, right, right, right. Did you ask him? Because you took, I mean, you took a course with him, and yeah, but I mean, you did a course with him, right? And you did a project, and you liked the project. What a better way to get a project and like, you did a reference, because this is not my material. I have no idea what's going on. Where this guy needs to work. I mean, you can just take 10 minutes and say this is good work or bad work. But I don't have no. Yeah, but the techniques you used are from the course, right? I mean, how far away are you from the course? It's very, yeah, but tell us. He knows the material. I mean, and,